Welcome back, physics fans. Here we go on graphing. This is just constant velocity graphing. So we're on a distance time graph. In this case, we could have made a displacement time graph with a direction, but that is a different version of this graph. So let's just, sorry, my scroll bar ain't working. Let's just close that and open that up again. Scroll bars are good when they work. So what is the average speed during the following times? So we're starting at 0 and we're going to 10. Now this really should be displacement because distance, or at least position, maybe this should be position. Because we're saying, and we're measuring from the 0 point all the time. So I would rather you just rewrite that word as a position time graph. From 0 to 1, the distance changed is 10 and it's 1 second. So the speed is d over t. So that'll be 10 over 1. So I'll write down the first couple ones. So that's 10 meters per second. Okay? And if this was a vector, we would get the direction from this writing here, not distance, but if it said position, it would have probably said meters and maybe north. So then we would also respond with north if it was a position time graph. This is not fully set up properly, so I won't push us that way. 1 to 2, here we go. We go from 10 to 6, that's a downwards of 4 over 1 second. That is negative 4 over 1, so that is negative 4 meters per second. But if this was a one with a direction as I had here, we would actually be going south here, positive 4, but we're not doing that right now. 3 to 4. So from this position here to this position, we go down 1 over 1 second, so that would be just negative 1 meters per second. From 5 to 6, we are flat-lined here. Flat line means you are not moving on a displacement time graph because your position is not changing. You're not going up or you're going down, so it's still 0. And 0 is 0. And now if you're wondering what direction would you do, you wouldn't put a direction. A zero-length vector doesn't have a direction. E, 7 to 8 seconds. We go 7 to 8, it went over 1, but rose 2, so it's 2 over 1. So that's going to be 2 meters per second. And from 9 to 10, it's going to be the same slope. If you want to observe, instead, if you want to do a little bit of understanding, this is a straight line all the way along. It hasn't changed its slope. It doesn't change its slope. So the slope from there, also the slope here, and also the slope there, all the same. So if you've done one of the calculations, then you do them all. And if this was a measurement one, not where I just drew perfectly straight lines, but if there was a measurement, you would always try to calculate the slope from the one end to the other end and try to get the maximum change over each of them so that you get a little bit more precision. I wouldn't want you to try to calculate a little slope here. That doesn't give you much precision. So that is, again, 2 meters per second, the same as above. So now 1 to 3, this is a little different because all these ones, the green line drawn on the graph was given to you as the constant velocity from that 1 second. And all these time frames were 1 second. But now I'm going over to 2 seconds. So from 1 to 3, you have to picture a line. Now don't draw this line every time. That would be getting kind of crazy, especially with how much I've asked you to there. But that you have to picture that line exists. And if not, you get the final minus the initial. So that line does exist, and that'll mean a run of 2 and a rise of negative 5. Okay, so this is negative 5 over 2, so this is negative 2.5 meters per second. Any questions? Okay, I'm just going to erase things because things are getting cloudy already. It's just, there's so much stuff there. Okay, next one. So from 3 to 9, we're going from 5 all the way up to 7. So this is a rise of 2 over 6 seconds. Now you didn't have to look on the graph. It's 9 minus 3, which would be 6. So this is 1/3, 0.333 meters per second. Okay, 4 to 10, you're going over to 10, so that's 6 that way, and vertically you're going up 5. 1, 2, 3, 4, 5. So I'm going to use my eraser to get rid of all my doodles there because I don't want to just keep doodling all over the place and make it quite a mess. So this goes up 5 over 6. So that is 5, 6. I'm not going to check my memory this morning. And Mr. Calculator says 5 divided by 6 is 0.83. And I'll just put 3 sig figs down. I don't know why. 1 to 9, you're starting off at 10, and you're going over to 7, so it goes down 3 over 8. So this is 3 over 8, and it'll be down 3. So that answer is going to be 3 divided by 8, 0.375. What did I forget? The negative. Okay. And 3 to 7. Going from 3 to 7, you're going down 2 over 4. So it'll be negative 0.5 and 0 to 10. From there to there, you're going up 9 over 10. So that's going to be 0.9 meters per second. Now there's some good questions down below. Okay, if you're just on the internet and don't have the worksheet, just take a quick snapshot of those pictures and come back to this time frame at 6:50 into the video. And here are the questions. What was the average speed for the whole trip? Okay, well, the average speed for the entire trip took 10 seconds. The average speed is this answer. Whoops, wrong pen. Okay, during which time frames is the object stopped? Okay, now it is a good challenging question here. We definitely know that it stopped here because your position isn't changing. So from the time frames, you could say from 5 to 7. Okay, from 5 to 7. But is the object stopped here? Is the object stopped here? Okay, it is actually argumentative, is it? Mathematically, it isn't. Mathematically, the slope at that point is undefined. To have an object stopped, the slope of a dt graph, that's what we're on, if it is going to be stopped, the slope of a dt graph has to equal 0. And the slope at this point here is undefined. As it approaches this way, the slope is 10. As it approaches this way, the slope is negative 4. That's the best we could do. Now, in physics land, nothing can instantly change from one speed to another speed unless it had 0 mass. And if it has 0 mass, then usually it's traveling at the speed of light. So we don't graph distance time graphs very easily with the speed of light. So in physics land, unfortunately, this graph does not exist. We are using this as a learning tool. In physics land, this graph doesn't exist. For instance, we can't be instantly stopped for 2 seconds and then instantly going at 2. In physics land, as you zoom in here, let's just pretend that we're zooming in here, or actually I will zoom in, 500, boom. I missed it. There we go. Let's erase all my mess here. We have to zoom in a million times more, and we can't. If this was an actual object, we would expect at least a little bit of a curve before it flattens out. It would need a little bit of time to change its speed up. There'd have to be a bit of a curve. And a curved line meaning acceleration. An object can't go from one speed to another speed without passing through all the other speeds in between, because that's what an object with mass has to do, as we learn later on. So in physics land, this graph that meets at a point doesn't exist. So we're just using this for training purposes. Yes, get angry at me. Yes, stop the video right now. You don't want to watch any more YouTube videos that are lying to you. During which time frames does the object have a negative speed? A negative speed would be from 1 to 5. Which time frames does it have a positive speed? It would be 0 to 1 and 5 and 7 to 10. 0 to 1 and 7 to 10. What's the total displacement? Change in distance? Change in position for the entire trip. The total displacement is 9 meters, because it's final minus initial. Initial is 0, final is that. So the change in displacement is 9 meters. Now, you should have a direction, and of course the next worksheet will. Okay, now, question 6b, you didn't do it. I don't know why you didn't do it. Oh, probably because it didn't exist. 6b, what is the total distance? Total distance traveled, not the total displacement traveled. The total distance. Oh, question 7 is that. Oh, okay, good. Oh, I'm reading again the other one. My bad. Number 7. So what is the total distance? 23 meters. So now that we have these totals, my bad, what is the average velocity and what is the average speed? Average velocity, we've already asked, and then average speed for the entire trip. See, that's why I had to change it. Average velocity will be 9 over 10 meters per second north, if this was so 0.9. And the average speed is total distance, 23 meters over 10 seconds, or 2.3 meters per second. So, what is the average speed for the whole trip? Even though I said it was 0.9, I lied. It's 2.3 meters per second is the average speed. And the average velocity is 0.9 meters per second. Now, I hope to have a direction from this position time graph. As I said at the beginning, I would love to have put N there for north, and then I'd have as a vector, and I'd feel comfortable. Thank you very much.